This is a stochastic processes, Model 7 Brownian motion and its applications. Lecture 4 Ito calculuses, Ito integrals. In the last 3 lectures, we have discussed the definition and properties of Brownian motion in the first lecture. In the second lecture, we have discussed geometric Brownian motion and the other process derived from the Brownian motion and their properties also. In the third lecture, we have discussed stochastic differential equations. In this lecture, we are going to discuss Ito integrals. First, we are going to start with the definition of Ito integral. When we say the stochastic process is Ito integrable, then we are going to discuss what is Ito process. Then followed by these definitions, we are going to discuss few examples. Followed by the examples, we are going to discuss the properties of Ito integrals. So with that, this lecture will be completed. This is the definition of Ito integral. Let xt be a stochastic process which is adapted to the natural filtration f of t of linear process Wt. That is xt be a ft measurable. Define it, I of t, that is nothing but integration between the limit 0 to t x of u, integration with respect to wu, where t lies between 0 to capital T, where t is a positive constant. I of t, a stochastic integral with respect to a Vernier process. The above integral is called the Ito integral. A detailed interpretation and the motivation of this can be found in the reference books. So the Ito integral I of t is defined in the form of integration 0 to t, and the integrand with respect to the integral with respect to the Vernier process W of t. The Vernier process already discussed. The Vernier process or Brownian motion is discussed in lecture 1. You can find in lecture 1 what are all the properties of Vernier process and so on. So the Vernier process Wt is starting with the standard one W0 is equal to 0, and it has increments are stationary as well as independent, and the increments are normally distributed with the mean 0 for the standard Vernier process, and the variance is a increment the difference. For s is less than t, it is the variance is t minus s. So here we have a stochastic process xt, which is defined between the interval 0 to capital T. The same stochastic process is adapted to the natural filtration f of t. Already we know that the Vernier process is adapted to the Wt, and here xt is also adapted to the Wt. That means for fixed t, xt is a ft measurable. That means the sigma field generated by the xt for fixed t will be contained in f of t. That means the information accumulated at time t, that is sufficient to find out the value of x of t for fixed t. So the xt is ft measurable for all t between the interval 0 to capital T. Then we can define this integral will be, call it as a Ito integral. So the xt has to be ft measurable, and ft is a natural filtration for the Vernier process Wt, then for all values of t between the interval 0 to capital T, I of t is called the stochastic integral, because this is not the usual integral, this is a stochastic integral with respect to the very near process Wt. This is a definition of Ito integral. Now we are going to discuss the Ito process. Let Wt be the Brownian motion and Ft be the associated natural filtration. A Ito process is a stochastic process. Xt is of the form xt is equal to x of 0 plus 0 to t integration delta t delta u d of wu plus integration 0 to t theta u du. So here we have two types of integration. The one type is the usual Riemann integration. The other one is the Ito integral, where x of 0 is a non-random and delta of u as well as theta of u are adopted process, and the delta of u is a mean square integral. If this condition is satisfied, then we can say this xt is going to be a Ito process. For all t, if you are able to write xt is of the form the one Ito integral and the Riemann integral, and both the integrands are adopted process, that means x of u is fu measurable as well as the theta of u is fu measurable, as well as the delta u is a mean square integral. That means the integration 0 to t expectation of a delta square u du is a finite value. Then we say it is mean square integral. If these three conditions are satisfied by the x naught, delta u, theta u and another, we can say the xt is going to be a Ito process. Once it is a Ito process, you can write down in the differential form, that is a stochastic differential equation, because we have d of w u. In the differential form, it will be, because delta t is equal, xt is equal to x of 0 plus integration, therefore in a stochastic differential form it is a dxt is equal to delta t times dwt plus theta t times dtt. So this is the stochastic differential form of Ito process. It means whenever delta t as well as theta t both are adopted process and x of 0 is non-random as well as delta t is mean square integrable, then the stochastic process written in the stochastic differential form dxt is equal to delta t dwt plus theta t dt will be call it as a Ito process. So the Ito process is nothing but a stochastic process, is of this form as well as satisfying these conditions. The way you write the stochastic differential equation, dxt is equal to delta t times dwt plus theta t times dt. Therefore, if you see the sample path, it is going to be the continuous function. Therefore, all the stochastic process with no jumps are actually a Ito process. Whenever you see the Ito process, you won't find the jumps. A jump Ito process is nothing but a Ito process in which the moments are discrete rather than continuous. So all the stochastic process with no jumps are actually a Ito process, because it has the term of dt as well as a dwt terms for the increment of dxt for all t. Ito integrals as well as the Brownian motion are the examples of Ito process. The way the previously written I of t as well as the Brownian motion, both are called the Ito processes. Now we are going to discuss the Ito integral. If xt and wt are not stochastic process but rather deterministic functions, then the situation is different. Assuming f of s, that means we discussed in a deterministic situation, we return integration is 0 to t g of s d f of s, where f of s is a differential function and g of s is the smooth function. Since it is a differential function, you can write d of f of s as the f dash of s ds, which is nothing but the Riemann integral. Whenever xt and wt are non-stochastic processes, rather deterministic functions, then you can write down this integration as a g of s df of s, that is nothing but the Riemann integrals. But in our situation, the f of s is not a differential. We can still define the integral. Remember that the wt, which is a nowhere differentiable, as well as a unbounded variation. So here we are going to discuss when f of s is not differentiable as well as when f is bounded variation, then still the integral is well defined. Further, if the function g of s is extremely fluctuating at different points in time, the limits may still diverge. When f of s is bounded variation, we can prove that the integral is well defined. Further, if the function g of s is extremely fluctuating at different points in time, the limit may still diverge as s tends to infinity. Since f of s is bounded variation, one can prove that the limit exists as long as g of s is not varying too much, and it is given by the integration 0 to t g of s df of s is nothing but limit n tends to infinity, summation of I is equal to 0 to n minus 1 g of si integration with the difference f of s plus f of si plus 1 minus f of si. That means since the integration is with respect to d of f of s, so you can find the difference f of s plus I minus f of si, then multiplied with the g of si, and that means you are partitioning the interval 0 to t into n parts. Then as n tends to infinity, that summation limit n tends to infinity will be the integration. Since f of s is bounded variation, you can prove that the limit exists. Remember that in the integral 1, that is this is integration, the Ito integral I of t x of u is a random variable for fixed u, w is a random variable for fixed u, and wu is a nowhere differentiable as well as a unbounded variation. Now we have discussed what is the situation if f of s is a bounded variation. The integration with respect to f of s, where f of s is bounded variation. Whereas our Ito integral xt and wt are stochastic processes, as well as wt is unbounded variation and nowhere differential. So that's the difference between the Riemann integral and the integral which we have discussing now, that is Ito integral. The integrand is x of t. The integration with respect to wt, where wt is a unbounded variation as well as nowhere differential. Whereas the Riemann integral which we have discussed, the f of s is differentiable, as well as later we discuss f of s is a bounded variation. Whereas the Ito integral, wt is a unbounded variation as well as wt is nowhere differential. Hence, it is different from the Riemann integral. So in the Riemann integral, the integration with respect to the function which is a bounded variation and it is differentiable, whereas here in the Ito integral it is unbounded variation as well as nowhere differentiable. Now we can rewrite the Ito integral 1 in the above form, in the following form. I of t, that is nothing but the way we have written in the above form, Riemann integral, integration with respect to integration of 0 to t, g of s with respect to f of s is limit n tends to infinity. The same way you can write I of t is limit n tends to infinity, summation I is equal to 0 to n minus 1, because the integration is the integration 0 to t x of u d of w, therefore it is x of si and the w difference, that is w of si plus 1 minus w si. The way we have written the Riemann integral, in the same way we are writing the Ito integral, where xt is a adapted process and wt is a stochastic, wt is a Vernier process or Brownian motion, and xt is adapted to the f of t, and the Ito integral I of t can be written as a limit n tends to infinity, the summation form. Here, since the expression on the right hand side is the sum of n random variables, therefore the limit here refers to one of the mode of convergence of a sequence of random variables, that is a limit in the sense of probability in distribution almost surely or in orth mean. When we can say the Ito integrable, whenever we have a stochastic process is Ito integrable, it has to be adopted, that is measurable, as well as it should be a mean square integrable. If these two conditions are satisfied, then you can say the stochastic process is Ito integrable. And the Ito integral which we have discussed in the first line, I of t is equal to integration 0 to t x of u dwt. So a stochastic process is called the Ito integrable on the interval 0 to t if it satisfies the first condition is it's adopted, that means x of s is f of s measurable and it is mean square integrable, that is integration 0 to t expectation of x square s ds has to be finite. Now we are going to discuss a few examples. Through that we are going to study the Ito integrals. First we consider the simple situation. Consider the Ito integral for a simple integrand function. That means for example you can see the illustration with the price may be negative. Let Wt be the price per share of asset at time t, and xt be the number of shares taken in the asset at time t, and ta be the trading dates of an asset. Assume that xt be a simple process. That means it takes a constant value in the interval ti to ti plus 1. The gain or loss, there is a possibility the price may go down and so on, maybe negative also. So with that assumption, the gain or loss from trading at each time can be viewed as a I of t, because I of t is nothing but integration 0 to t x of t dwt. Therefore, the gain or loss from trading at each time can be viewed as a I of t. So since it is a simple process, you can write it x of t comma w, where w is belonging to omega. You can write down the simple process in this fashion, where psi a be the bounded random variables such that psi naught is f naught measurable and psi a's are f ti minus 1 measurable, because it is taking a constant value between the interval t. It takes a constant value between the interval ti to ti plus 1. Therefore, you can write down the simple process x of t in this form. So for a simple process x of t, the stochastic integral I of t, that is nothing but the gain or loss, that I of t is nothing but the integration 0 to t x of s d of ws, that is nothing but limit p tends to infinity of I is equal to 1 to p psi I multiplied by the difference of wi's. In this limit, the first term of the above equation, that is psi naught pi naught y indicator function of t, does not contribute anything, hence w naught is equal to 0. In particular, if you take x of t is equal to 1 for all the interval, then the psi a is equal to 1 for all the interval. Therefore, the I of t is nothing but, since x of t is equal to 1, you are just integrating 1 with respect to ws. Therefore, you will get wt. We calculated Ito integral for a simple integrand. As a general integrand can be expressed as the limit of simple integrands. Therefore, the Ito integral of general integrands can be obtained by taking the limit of sequence of Ito integral of the simple integrands. This is a simple situation in which integrand is a simple function. Suppose the integrand is a deterministic function, not a random. The delta t is not a random. Now we are defining the Ito integral I of t, that is 0 to t delta of s dws. Since expectation of I of t is nothing but a I of 0, that is equal to 0, because the Ito integral satisfies the martingale property. This we are going to discuss at the end of this lecture. The Ito integral is going to be a martingale. So this property is used here. Otherwise, we can directly find out expectation of I of t, that you will end up 0, or by using the martingale property it will be I of 0, but I of 0 is equal to 0. You can find out the variance of I of t also. For that you have to find out expectation of I square of t, that is nothing but expectation of 0 to t delta u of dws. Then you can find out the expectation of I square t, so that will end up delta square of s ds. So using this you can find out the variance. Variance is equal to expectation of I square t minus expectation of I of t whole square. Since expectation of I of t is equal to 0, therefore variance of I of t is same as expectation of I square of t, that is 0 to t delta square s ds. Or you can use the isometric property for finding the expectation of I square, that is same as 0 to t expectation of delta square s ds. Since delta t is a non-random function, the expectation of delta square s is same as delta square s. So one can use the definition and find out this expectation, or you can use the isometric property and use the expectation of a constant is same as a constant, therefore it is 0 to t delta square s ds. So in this example we are finding the expectation and the variance of I of t. But you can find out the distribution of I of t also. You can find out the distribution using moment. So find out the moment generating function of I of t. You know that a moment generating function for any random variable is nothing but expectation of e power u times x. So here you are finding the distribution of the random variable I of t for fixed t. Therefore, it is expectation of e power u times I of t. You can find out this value is e power of times u square integration 0 to t delta square s ds. So once you are able to find out the moment generating function for fixed t, you can compare the moment generating function of some standard distribution. Then you can conclude what is the distribution of I of t. Here the moment generating function is e power of u square integration 0 to t delta square s ds. So this is same as the moment generating, this is of the form the moment generating function of normal distribution. Therefore, we can conclude for each t, I of t is normally distributed with the mean. Now you have to compare this moment generating function with the moment generating function for function of normal distributed random variable with the mean mu and variance sigma square. By comparing the MGFs, you can conclude what is the mean and variance of I of t. So here you will come to the conclusion the I of t is a normal distributed random variable with the mean 0 and the variance is integration 0 to t delta square s ds. For fixed t, it is normally distributed. So in this example, we are finding the mean and variance of I of t as well as what is the distribution of I of t also. We are finding the mean and variance as well as the distribution of I of t when the integrand is non-random function, of time. Third example, here we are evaluating the integration 0 to t, integrand is w of 1 dwt. Note that w of 1 is not adapted to the filtration, that is f of t. Sigma of ws for the interval 0 to 1. As the t increases from 0 to 1, w1 is not adapted to the filtration f of t, where f of t is the natural filtration of Vernier process. So since it is not satisfying the condition of integrand is adopted, therefore this is the Ito integral does not exist. So this example shows that the assumption of integrand is adapted to the filtration is needed to have the existence of Ito integral. So here the Ito integral does not exist. We are moving into the next example. Evaluate the Ito integral, integration between 0 to t, wt, dwt. That means the integrand is wt, integration with respect to wt. So we can use the partitioning the interval 0 to capital T into n pieces, n parts. Then as a limit n tends to infinity, this is not, the integration is nothing but limit n tends to infinity of I is equal to 0 to n minus 1 w of ti and the difference of w's. So the same definition we have given in the Ito integral also. So here the Ito integral is well defined because wt, that is the integrand which is adopted, and also the mean square integrable. Therefore this is Ito integral. So the I of t is equal to 0 to capital T wt, that integral is the Ito integral. But here we are going for the upper limit is a capital T, not the variable limit. So for each I, the way we have written limit n tends to infinity summation with the difference of w's I and w's, and this is a w at the point ti, and whereas this one is a w of t I plus 1 minus w of ti. Therefore these two are the non-overlapping w's, so the increments are independent. Therefore w of ti and w of ti plus 1 minus wa are the independent random variables, or having the normal distributions. We are using the property of Brownian motion. Therefore w of ti and w of ti plus 1 minus wa are independent random variables. So what I am going to do here, let pi be the set of all finite subdivisions of pi of the interval 0 to capital T. Therefore first we will find out what is the q of pi. That is different from what we want. What we want is different. What we want is limit n tends to infinity summation I is equal to 0 to n minus 1 w of ti with the difference. But what we are defining now, q pi I, is nothing but the difference whole square. But what we want is this w of ti with the w of ti plus 1 minus wti. So we started with the q pi, that is equal to the difference whole square. The difference whole square is the same as suppose you treat this as a, this as a b. So a minus b whole square is same as a square minus b square minus 2 times a b minus sorry a minus b minus 2 times b a minus b. So if you simplify, you will get a minus b whole square. But if you expand the summation now, this will be only the last term will be there and all other terms vanishes. So therefore you will get a w of t whole square minus w0 whole square. The last term and the first term will exist and all other terms will vanish because of minus squares. Whereas this one, minus of 2 summation w of ti multiplied with the w of ti plus 1 minus w of ti. That's what we want as a n tends to infinity. But we know the result, limit norm of pi tends to 0 of q pi will be capital T. That we have discussed in the lecture 1 when we discussed the quadratic variation of Brownian motion. In the lecture 1 we have discussed the quadratic variation of Brownian motion. In that q pi is defined, limit norm of pi tends to 0, the q pi will be capital T. Therefore what we want is a limit n tends to infinity of this quantity, and that is in the third term in this q pi. So now you apply limit n tends to infinity in this equation. So the left hand side becomes the capital T, the right hand side becomes a wt whole square minus w0 whole square. You know that w0 is 0 for a standard Brownian motion. Therefore you will get only the first term, second term will be 0, third term is the unknown. That's integration. Limit n tends to infinity of summation, that is nothing but the I of t, I of capital T. Therefore 0 to capital T wt dt, that is nothing but in the left side we got a capital T. Therefore you will get wt whole square minus capital T is equal to, since it is minus 2 times, therefore it will be by 2. Hence the integration 0 to capital T wt dt becomes a wt whole square minus capital T by 2. So here we have used the quadratic variation of Brownian motion is capital T, that we have used for the interval 0 to capital T. Therefore, the integration is 0 to capital T. So, we have used the Brownian motion quadratic variation between the interval 0 to capital T, that is capital T. Therefore, the integration is going to be W of capital T whole square minus capital T by 2. Hence, this integration is Wt whole square minus T by 2. We see that unlike Riemann integral, we have extra term capital T. If the integration is with respect to bounded variation differentiable function, then you won't have the term capital T here. Just it is a Wt whole square by 2. Suppose you replace Ws by x, therefore you will get a 0 to capital T x times x dx, that is nothing but x square by 2. Whenever the integrand is a bounded variation as well as a differentiable function, that is nothing but the Riemann integral. So, in the Riemann integral you won't have the extra term capital T by 2, but here we have the extra term minus T by 2. So, this arises from the quadratic variation of a Brownian motion, which is finite. Whereas, if it is a real valued function which is bounded, then the quadratic variation is going to be 0. But here the quadratic variation which is finite value, therefore you are getting minus T by 2. So, the above next remark, the above integral is defined not only for the upper limit integration capital T, but also every upper limit of integration between 0 to capital T. In this integration, we have done the upper limit is capital T. Therefore, we have used the quadratic variation of Brownian motion between the interval 0 to capital T, that is capital T. But instead of that, we can go for variable small t also. In that case, here we have to use the quadratic variation of Brownian motion between the interval 0 to small t, and that will be small t itself. That's a variable t. Therefore, this integration will be 0 to small t, Ws dws is nothing but Wt whole square minus a t by 2, where both the t's are small letter variable. You see, the construction of Ito integral is similar to one of the Stieltjes integration, but instead of integrating with respect to the deterministic function, the Ito integral with respect to the random function moves precisely path of linear process. So, that is the difference between the Ito integral and the usual integral. The usual integral is with respect to the deterministic function, whereas in the Ito integral, the integration with respect to the path of Brownian motion or linear process, which is unbounded variation and nowhere differential. Therefore, the whole integration is different. Consider this stochastic integral. In this, the first integral is a Riemann integral of a stochastic integrand, whereas the second integral is a Ito integral. This equation is very useful in finance. In the Black-Scholes model for pricing, the stock price is assumed to follow geometric Brownian motion. Now, we are discussing the few properties of Ito integrals. Still, we have used a few properties in the examples, but now you can understand how the properties will be used in the examples. The following results holds by the Ito integral defined in the equation 1. In the equation 1 we have discussed this is the Ito integral which we have discussed in the first equation. So this we are referring. Yes, the first property, the integral I of t is a martingale with respect to the filtration f of t. This is a very important property. If you have a Ito integral, that means the integrand is adopted and mean square integrable, and the Ito integral is a stochastic process, and that stochastic process is having the martingale property with respect to the filtration f of t. The same f of t, the integrand is adopted also. With respect to the same filtration, the integrand is adopted also. So the proof is you have to, if you want to verify the stochastic process is martingale, you have to check three properties. The first property is it has to be first the stochastic process for fixed t, it has to be integrable. Then it has to be adopted. Then the third property, the conditional expectation has to satisfy the equality property. So if these three properties are satisfied by the stochastic process, then we say the stochastic process has the martingale property. So here I of t is a stochastic process for t greater than or equal to 0. So first we have to verify it is integrable. So you can find out the expectation of I of t for every t. That is going to be a finite value. Then the second one, I of t has to be for fixed t, I of t has to be a ft measurable, that is adopted. So for fixed, already the integrand is adopted. The integration with respect to wt, and the wt is also adapted to f of t. One can prove the I of t is also adapted to the filtration f of t. The third condition, expectation of I of t given f of s, where s is less than t, that is same as I of s. You have to prove expectation of I of t given f of s, where s is less than t, that is equal to I of s. If that is proved for all t, since these three properties of martingale is satisfied, I of t will be a martingale with respect to the filtration f of t. Here I am not discussing the proof. Here I am not giving the proof, but I have discussed what are all the properties has to be verified. Second property, expectation of I of t, that is same as the expectation of 0 to integration, the definition, that will be 0. Since it is a martingale, it will have a constant mean. Therefore, expectation of I of t is same as expectation of I of 0, and you know how to evaluate expectation of I of 0, that will be 0. And the third property, expectation of it whole square, that is same as expectation of 0 to t x square ds, that is same as expectation of integration 0 to t expectation x square s ds. So the expectation and the integration interchange the place. This is called the Ito isometry. So this is a very important property of second order expectation, that is the integrand, and earlier you have expectation of I of t whole square, that is nothing but integration 0 to t expectation of x square ds. This is nothing but the Riemann integral. For fixed s, the expectation of x square s is the function of s. So you are integrating 0 to t the integrand is expectation of x square s ds, so this is nothing but the Riemann integral. Now based on the property number 2 and 3, you can conclude variance of I of t is nothing but 0 to t expectation x square s ds, because the expectation of I of t is equal to 0, expectation of I of t is equal to 0, therefore variance is nothing but expectation of I of t whole square minus expectation of I of t, variance of I of t is equal to expectation of I of t square minus expectation of I of t whole square, that is same as 0 to t integration expectation of x square s ds. One can find the quadratic variation of I of t also, because I of t is a stochastic process. So you can find out the quadratic variation between the interval 0 to t. So I comma I between the interval 0 to t, that means a second order variation between the interval 0 to t for the function I of t. I of t is the Ito integral, whereas the quadratic variation is nothing but integration 0 to t x square s ds. So this is the Riemann integral. So I have not given the proof of the fifth property also. We are just stating the results of Ito integral, and we have used a few properties in the examples. The Ito integral is a random variable for all t, for all w belonging to omega. Therefore, you can write down I of t of w, that is nothing but a limit n tends to infinity, the value of x of si, the difference of w's. You know that x is a random variable, the difference of w's is also a random variable. Therefore, for fixed n, this summation I is equal to 0 to n minus 1 will be nothing but a random variable, and you are finding limit n tends to infinity of the summation. Therefore, actually the convergence takes place only for the subsequence. That means I of t is a random variable, and that random variable is nothing but the convergence of the right hand side limit n tends to infinity of the summation, and its integral depends on the sample path, because you are finding the difference of w of si plus 1 minus w of si. Therefore, this integral depends on the sample path. And also we need this following properties: the d of wt dwt will be dt, that is nothing but the quadratic variation of Brownian motion is nothing but a finite value. If you are finding the increment between the interval 0 to t, then the quadratic variation is small t. Whereas if it is a real valued function, which is a differentiable, then dt, the quadratic variation of the function t will be 0, and the mixed variation, cross variation dwt with the dt, that will be 0. So if you find out the quadratic variation with the wt, that will be the t, whereas the quadratic variation with the function t will be 0, and the cross variation will be 0. So this result will be used when you are finding the I of t. Here is the important references for the Ito integrals. In the next class, we will consider the Ito formulas.